Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 10 on the orthocenter of a triangle. So we've been talking a bunch about what are called points of concurrency, and the orthocenter will be another one. So let's get kind of right into it and talk about the orthocenter. Points of concurrency. We've now seen the circumcenter and the incenter as 2 points of concurrency. In this lesson, we will learn about our last one for now, known as the orthocenter. Unlike the other two, this point of concurrency does not have an associated circle with it, which probably makes you wonder why it's called a center in the first place. Anyway, it's found by constructing altitudes. So before we kind of move on, let's remember what an altitude is. An altitude of a triangle is a line drawn from one vertex perpendicular to the opposite side. The opposite side may need to be extended if the perpendicular does not intersect with it. All right, so altitudes are very, very important for triangles because they're oftentimes used to calculate or to help calculate the area of a triangle. All right, and they're very simple, right? So let's take a look at exercise 1, and we'll talk a little bit more about altitudes while looking at exercise 1. In triangle ABC shown below, altitudes have been drawn from points B and C as shown. The altitudes intersect at point M. Construct the altitude from point A to BC, label its intersection with BC as point F. Verify that it passes through point M. All right, so in other words, an altitude is always a line or line segment that goes from a vertex like B perpendicular to the other side. So BD is perpendicular to AC, so BD is the altitude drawn from B to side AC. CE is the altitude drawn from C to side AB. All right, now what we're going to do is we're going to draw the third altitude, or we're going to construct the third altitude specifically from point A to side BC. Now we've done a little bit of this before, especially when we worked with the in-center, right? Because what I want to do is I want to construct a line that passes through A that is perpendicular to side BC. So let's remember how to do that. All right, let's take a look. So what we're going to do to construct a line that passes through a point not on the line and is perpendicular to a line is I need to first put my compass center at the point that I want to draw the perpendicular line through. And I want to then, whoops, that's not going to be quite long enough. I want to draw an arc that passes through that line twice. I can't quite get it long enough, which is weird. Okay, that should be long enough. Yep, that'll do it. All right, so centered at A and passing through side BC twice. Now what I'm going to do is I'm going to bring my compass down, right? Maybe extend my page a little bit, bring my hypercube down there to keep the page extended. All right, I now need to put my compass point on one of those two intersection points. Bring it out here, maybe make it a little bit wider and make sure it's really on that intersection point. Draw that arc, move the point of my compass to the other intersection point, and draw this arc. Okay, in theory, if I draw a line through A and through that intersection, it should be perpendicular to BC and passing through A. All right, not bad, not bad. All right, there it is, right, nice and perpendicular. Let me move that out of the way so I can draw my right angle symbol. And what did they want me to do? Label that intersection point as F and verify that it passes through point M. And there it does. And therefore it's a point of concurrency, all right? That point, the point where the three altitudes of a triangle intersect, and they will all intersect at one point, right? That's the idea of a point of concurrency, is called the orthocenter. In math, ortho basically means perpendicular. Now, you could ask, well, why don't they just use the word perpendicular? I don't know. Maybe because perpendicular is not a prefix, whereas ortho is, right? But literally, the word ortho means perpendicular, okay? So where the three altitudes intersect is a point of concurrency, and it's called the orthocenter. Now, unlike the circumcenter or the incenter, and maybe you'll like this about the orthocenter, there's no point at which time I'm going to put the center of my compass right there and draw some funky circle that goes somewhere. I'm just locating the orthocenter. Okay, that's absolutely it. So let's kind of keep going. Let's take a look at the orthocenter. Okay, the orthocenter of a triangle. The lines containing the three altitudes of a triangle intersect at a point of concurrency known as the orthocenter. The intersection of any two of these lines uniquely locates the orthocenter. Like the circumcenter, the orthocenter will not always lie on the inside of the triangle. So remember, at this point, right, we have 3 points of concurrency: the circumcenter, the incenter, and the orthocenter. The incenter always lies inside of the triangle, but the circumcenter can either lie inside or outside of a triangle. So let's take a look at another problem. Exercise number 2. Construct the orthocenter of triangle KLM shown below. You will need to extend at least one of the three sides in order to locate this point. Label the orthocenter as point O. All right, now you can kind of understand where I'm coming from here, right? Now it's easy to see that we can draw a line that passes through M that is perpendicular to side KL, right? That's simple enough. But if we were to draw a line from K perpendicular to ML, it wouldn't actually intersect segment ML. That's okay, I just need to extend segment ML, all right? But first things first, let's construct a line that passes through M that is perpendicular to side KL. Let's construct that particular altitude. All right, so here we go. Let me bring my compass down here. Let me put the sharp point at M. Let me expand it. Whoops, let me keep the point at M. All right, again, all I want is to make sure that line is going to intersect KL twice. It will. There we go. Now that I've got that intersection twice, I can come up here, put my compass like that. I can change the radius or leave it the way it was. Again, we also want an arc there. All right. Now I want to draw a line through M and through the intersection of that, and that should be then perpendicular to KL, and it looks perpendicular to KL. Now, one thing that's true about the orthocenter, which is a little bit irritating, is it can be all over the place, all right? And maybe so all over the place that I need to draw this line very long, okay? So I'm still not sure where the orthocenter is, but I know that it's going to be somewhere along that particular line because that is the altitude, or at least it contains the altitude from M to KL, right? Technically, the altitude is simply the segment from M to KL, but that line is going to contain it. Now, I have to draw a perpendicular to one of the other two sides, both of which, though, I would have to extend in order to get that perpendicularity. I think the most logical thing to do, I could extend either side, but the most logical thing to do is make this, oh my, is make this ruler a little bit smaller. I feel like it just zoomed in. Is bring this up and extend side ML, okay? So what I'm doing is I'm just making side ML longer, okay? And now what I'm going to do is I'm going to construct the perpendicular from K down to that particular line, all right? So just like what we did before. Pause the video now and catch up a little bit, extend this line, right, like this, and see if you can construct the perpendicular line that goes through point K and is perpendicular to this extended line ML. All right, let's go through it. So let me kind of come up here, again, putting my compass right there. Let me switch that orientation. All right, maybe make that a bit bigger. Good. Yep, that'll do it, right? I just need it to go through that line twice. There it is, and somehow my line moved on me. I'm gonna see if I can shift that back down. Not bad, not bad. I'll take it, it'll do. All right, now I wanna come down here. Again, put the pointy end of my compass at one of those intersection points. Oh yeah. You probably have an easier time of doing this than I do, given that you don't have to keep moving that thing around. But let me get it a little bit longer. There we go. There it is. Put it over here. And there we go. All right. And now we just have to draw that perpendicular line. All right. There is our altitude. I don't know why that didn't draw in there. We'll just kind of connect it like that, right? So I have an altitude drawn from K, perpendicular to side ML, and I've drawn that altitude from M, perpendicular to side KL, and where those two altitudes intersect is my orthocenter, which I think they said label as point O. So that's one of the trickier things about finding the orthocenter, is that if the triangle's acute, like in our last situation, we don't have to extend any of the sides in order to construct the altitude. In this case, we have to. In obtuse triangles, we have to do that. All right. And of course, this brings us to something that's probably pretty obvious, the location of the orthocenter. This is probably going to look familiar. Exercise number 3. Fill in the following. If a triangle is acute, then the orthocenter will lie blank the triangle. And if the triangle is obtuse, the orthocenter will lie blank the triangle. All right. Now, I know we just did one acute triangle and one obtuse triangle, but we're going to generalize from that. If a triangle is acute, the orthocenter will lie inside the triangle. And if a triangle is obtuse, the orthocenter will lie outside the triangle. I'm going to put a big star down here. That is exactly the same as the circumcenter. So if you go back and you look at our work with the circumcenter, what we found was that when we had an acute triangle, the circumcenter lied inside the triangle, and when we had an obtuse triangle, the circumcenter lied outside of the triangle. It's exactly the same thing with the orthocenter. Now, that does leave one type of triangle still to be talked about, which is a right triangle. And if you recall, with the circumcenter of a right triangle always lied at the midpoint of the hypotenuse of the right triangle, of the longest side, the side opposite the 90-degree angle. But what will be the location of the orthocenter of a right triangle? Well, let's tackle that as our last piece for the lesson. The orthocenter of a right triangle. Exercise number 4. Given right triangle EFG shown below, answer the following questions. Letter A. At what point would the altitudes from point E and F have to intersect? Explain. All right, so to find the orthocenter, you just have to draw any two altitudes of the triangle. So my question is, if I draw the altitude from E down to side FG or GF, if I draw the altitude from F to side EG, where would those two altitudes intersect? Pause the video now and maybe this will be obvious, or maybe it won't. Well, they'll intersect at point G, right? In fact, EG is already an altitude because it is perpendicular to FG, and FG is already an altitude because it's already perpendicular to EG, right? So they'd intersect at point G, and this is because EG and FG are already altitudes. Right, they're already altitudes. Because the altitude is simply a line segment that is drawn perpendicular to the opposite side. Well, EG is certainly perpendicular to FG, and FG is certainly perpendicular to EG. So this actually makes the orthocenter of a right triangle exceptionally easy, right? Letter B. Where will the orthocenter always be located in any right triangle? Well, it'll be located at the vertex where the right angle exists. That's it. The vertex, whoops, that's not vertex, that's vertex. Vertex of the right angle. Now the vertex, how about located at the right angle? It's not the vertex of the right angle, it's the vertex located at the right angle. Right? In other words, the vertex that has an angle of 90 degrees is in fact the orthocenter of the triangle. And it does seem a little bit weird because, of course, saying that point G is somehow the center of this triangle is very strange. Then again, also saying the midpoint of EF is somehow the center of that triangle, right? That would be the circumcenter, is also a little bit strange. But the orthocenter is very unique in that it is one of the more difficult ones to prove that it's a point of concurrency. We didn't even make an attempt at doing so other than demonstrating it in the first exercise. And it also doesn't have an associated circle with it like the incenter and the circumcenter did, all right? But like the circumcenter, we can really boil down where it exists, where the orthocenter occurs by whether the triangle is acute, in which case it's inside of the triangle, obtuse, in which case it's outside of the triangle, or a right triangle, in which case it's located right at the right angle. All right, let's summarize. So that was the last that we'll see of points of concurrency for a little while, right? And a point of concurrency is just where three or more lines intersect. We've now seen 3 points of concurrency, the circumcenter, the incenter, and today we saw the orthocenter. The orthocenter being where the 3 altitudes of a triangle intersect. Again, if it's an acute triangle, the orthocenter is located inside of the triangle. An obtuse triangle, it's located outside of the triangle. And in a right triangle, the orthocenter is located right there at the right angle itself. All right? Now, I wish I could say that you're going to see the orthocenter quite a bit in future lessons like I normally do at this point, but you likely won't. All right. It is important to know the 3 points of concurrency that we've learned so far and distinguish between them. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.